talk today about a model that we're developing in our lab to look at protein structure. So a lot of us have worked with different molecular dynamics or protein stimulation models before. These models have energy calculations that they do to determine what the protein structures will be. Their energy calculations often include terms for the bond lengths and bond angles, as well as terms for interactions between non-bonded atoms, such as repulsive terms and attractive electrostatics. These models typically also use knowledge-based terms to predict the dihedral angles found in the side chains. And they often have other terms, such as solvent polarization and hydrophobic effects, that they use to predict the most likely structures. As you can see, there's a fair number of terms that they can use to calculate their energy and their structures. Our goal is to develop a very simple model using just steric interactions and see if that is enough to predict some of the features we see in a protein. So our first goal with this is to be able to reproduce the side chain dihedral angle distributions. So a dihedral angle is an angle between four atoms. Here I have a valine residue, and your chi-1 side chain dihedral angle in valine is defined with the nitrogen, C alpha, C beta, and C gamma 1. When you're thinking about your dihedral angles, you can think about it as if you're looking straight down the bond between C alpha and C beta, where you can see down here, the gray circle would be your C alpha and your blue would be the C beta. And when you look at the bond in this way, you can then see the angle between your nitrogen and C gamma 1, which here is about 60, here would be 180, and here would be 300. If we look at the dihedral angles of different amino acids inside of a protein and inside different proteins, we can generate a distribution of the side chain dihedral angles. Here I'm showing the dihedral angle distributions of several different residues. We have a valine over here on the left, threonine, leucine, and isoleucine. These are a little hard to see, but here in valine we have 3 peaks, with the largest peak being at a chi-1 of 180. In contrast, on threonine, we also have 3 peaks, but the largest are at 60 and 300. On leucine and isoleucine, we have chi-1 and chi-2 distributions. And because of that, we plot it as a heat map, with the darkest regions being the most probable regions. So the goal of our model so far has been to try to predict the side chain dihedral angle distribution using simple sterics. So here we have kind of how our model works. In our model, each atom in the protein dipeptide is represented as a solid sphere. So a dipeptide would then be a combination of overlapping spheres. On the right here, we have a leucine residue with the carbons in green, our hydrogens in gray, nitrogen in blue, and oxygen in red. And as you can see here, we're rotating our chi-2 dihedral angle. As we do the rotations, different atoms, the atoms that move, we look to see if they're overlapping with any other atoms in the residue. If there is an overlap, we say that that dihedral angle is disallowed, which you can tell in here because I show it in red. But if there is no overlap, the angle is allowed. If we repeat this with all combinations of the chi-1, chi-2 dihedral angles in leucine, we will get a distribution that looks something like this, where there are a few regions of allowed dihedral angles, but most of the dihedral angles are disallowed due to overlaps. If we were to then repeat this with another instance of leucine, we would get a different plot. You can kind of see there's one spot down here instead of the 2 spots here. The reason for these differences is that there is a variation in the bond lengths and angles and the backbone configurations found in a protein peptide. To deal with these variations, we use a protein structure database called the Dumbrach database, which is a set of 792 non-homologous protein structures with resolution of less than 1.7 angstroms and less than 50% sequence identity. If we use this database and sample all instances of the residue, we can go from a single distribution for one residue and combine them to get a total distribution that takes into account the bond length and angle variations. So one other thing that we have to take into consideration consideration with this model is how big to make our atoms. If we make our atoms too large, we're going to always have overlaps, and we're not going to be able to see a distribution like this. But if we make them too small, we won't ever have any overlaps, and too many of our angles will be allowed. So to deal with determining the atom radii, we first set 12 different atom types inside of our proteins, which you can see here on the left. On the right are 3 different residues, color-coded to match the table. Here we have a valine residue, which has 2 different kinds of carbons, 2 different kinds of hydrogens based on if it's bound to a carbon or to a nitrogen group, and then the nitrogen and the oxygens of the backbone. On threonine, we add 2 more atom types. We have the carbon that's bound to an OH group and the oxygen of the OH group. And then on phenylalanine, we have 2 additional atom types, the aromatic carbon and the hydrogens of the aromatic ring. So in total, if we look at all of our uncharged amino acids, we have 12 different atom types. I then had to determine what the best atomic radii is to use for each of these. To do this, I tested a range of over 60,000 possible combinations of atomic radii. For each possible set of atomic radii, I determined the predicted dihedral angle distribution for the uncharged amino acids. Here is an example of what that would look like for valine, where I'm plotting 4 different dihedral angle distributions for 4 different sets of atom sizes. If you remember from a couple slides ago when I showed a valine distribution, we want to have one large peak at 180 and then 2 small peaks at 60 and 300. The atomic sizes used to create this blue and this green line don't give us this valley here, so we would consider that as a bad set of atomic radii to use. If we do this with all of the radii over all of these amino acids, we can determine what the best atomic radii is for the model. When I did this, I generated these atomic radii shown in this table. And the valine shown here on the right has each atom with the radii from the table. There are a couple of different things that we can see from the radii. First of all, if we look at our hydrogens, we can see that our hydrogens bound to a polar nitrogen or oxygen has a smaller radii than a hydrogen bound to a carbon group, which matches what we know about the electron density of a polar oxygen-hydrogen or nitrogen-hydrogen bond. We also see some similar things occurring with our carbons when we have an sp3 hybridized carbon versus an sp2 hybridized carbon, where the sp2 has a slightly smaller atomic radii in our model. Using this atomic radii, I'm able to generate dihedral angle distributions that fairly accurately match those found in crystal structure data. Here I have the plots of the chi-1 distributions for valine, cysteine, threonine, and serine. On each of these plots, the blue curve is the observed chi-1 distribution in the GEMBRAC database, while the red plot is the predicted distribution. For all 4 of these, you can see that the peaks are in the correct location and that there's a relative match of the peak heights. If we continue and look at some other residues, on the top here we have isoleucine, and on the bottom is leucine. Once again, you can see that in our observed distributions, we have several regions where the residue is allowed, it shows up in the observed distribution, and those are replicated in our predicted distribution for both of these residues. With phenylalanine and tyrosine, we once again have a similar result. Both of these residues are planar around their chi2 dihedral angle, which is why they're only plotted from 0 to 180 on the y-axis. And here you can see that we have our peak centers in the same location on both the observed and the predicted. So we now have a model that uses simple steric interactions to determine the dihedral angle configurations of the side chains. There's several applications that we have for this model. First of all, we are using the model and the atomic radii from it to determine the packings of protein cores. Some work has been done on this in the past, but typically without placing hydrogens on the side chains. So we are instead putting hydrogens on our side chains and studying how well-packed proteins are. And Professor O'Hearn will be giving a talk on that tomorrow. We've also started to use this model to do mutational studies, where we can see how a mutation at a protein peptide binding site will affect the number of dihedral angle configurations allowed by the side chains of the binding region. And we can use that to predict the effect of that mutation. So in conclusion, we've generated a model that does not use the knowledge-based terms or the attractive terms that are used in many protein simulations. Instead, our model uses a simply samples the dihedral angles allowed by the dihedral angles of a side chain and sees where clashes are present and when there are no clashes. And using this model, we've been able to replicate the dihedral angle distributions that are found in X-ray crystallography data. With that, I have plenty of time, I believe, for questions. I also am going to have a poster on this tomorrow.
Any questions?
What is the advantage of the steric approach over having like a dihedral angle potential?
So the steric approach allows you to really see what forces are actually at play in predicting the dihedral angles. And I believe many of the dihedral angle potentials are knowledge-based, so you look at crystal structures, you see that the most probable dihedral angle of valine is 180, so you set your potential to make it be closer to 180. Instead here, we specifically see what is allowed for a particular residue.
So in your title and sort of at the end, you address this issue of dense interior protein packing.
Yes.
What's that about? I didn't know there was a story around how densely the interior proteins are packed.
So there's been studies done to see how tightly packed protein cores are. And my PI is going to give a talk on that tomorrow morning. But in general, people have said that protein cores are as tightly packed as a crystalline solid, which we have kind of started to show that isn't necessarily the case.
What would it mean if it were or it weren't? Why would that be important, whether it's like a crystal or not?
It kind of tells you what forces are at play in generating the protein core, and if it is the packing, if the packing has a large role in that. And also, I feel like it would be relevant in other, when you're looking at protein folding, when you're trying to predict how a protein is going to fold, is to what level do we expect it to pack, and do we want to aim towards the packing?
Another question over here.
Hello. Is there a way you could extend this model to include charged residues?
So we've been working on trying to do charged. We haven't had quite as much success as we've had with uncharged residues. We think we might have to add some repulsive forces between the charged residues of the charged atoms in the side chain and the polar residues in the backbone.
Any other questions? Was there a question over here?
Yeah. So already answered.
Okay. If there are no more questions, let's thank Jennifer again.